And let's start the tutorials for today. Yeah. And I will go over like a format string challenges from the format string read to the arbitrary write. And then I will do either one of the like a 32 or 64-bit in each category so that you can do the counterpart of the exploit. Yeah. And then like basically what we will gonna do is like we will transform the format string variability into the arbitrary either sequential read or arbitrary write, either one of them. And then like we will use the tricks that we have used for the exploiting sequential read or arbitrary write as we like practiced uh, in these examples. Yeah. So that you can apply like the some of the techniques that you practice in these examples in these examples by like turning the format string variability into either a sequential read, arbitrary read, or arbitrary write primitives. Yeah. And then I will go over like either one of the challenges of the either 32-bit or 64-bit in each of the category. And let's start with the format string read one. Yeah. And then yeah, no, it's okay. Yes. All right, so the challenge asks us something. Then if we type something, then it asks us like the guess the random. And then if we type something, then it says like the random was this one, but what we typed is some of the wrong value. So it's just FFFF. And then like the program asks us to match this number. And then this is generated by random. So like we cannot just guess because just we have only one chance. But what we need to do is like the, and then if we take a look at the C code, you will see that it will get the random from the dev urandom, which is a somewhat real random from the Linux kernel. Yeah. And then the random value is here at the stack as a local variable. And then there's a read of our name, but there's no buffer overflow variability because the size is 64, while we can uh, type up to 63 characters. And then here's a format string variability. So our input directly goes to as the format string arguments of the printf. So it's like an intentional, the malicious use of the printf. And then it asks for like us to guess the random. And then if that matches to the random, then it will give the shell. So our task is like we need to figure out this value. Then if we just think about the stack configuration, something like, so suppose we have some of the ESP at here, and then called printf. Then this will be the format string. Yeah. And then there will be some other variables like this. But eventually, we could have our random number at here. And then if we can point this as a first, second, third, fourth, fifth, and sixth additional arguments, then if we supply something like %p, 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 %p 6 times, then we can get the random number at the end of this output. So this is our idea that we can catch from the nature of the format string variability. And let's try that. So they run the program, and then I will just type %p. And instead of the printing %p here, the printf interpreted this %p as a format string, and then it just printed out the first argument on the stack. Yeah. Then and at this time we don't know about the random, but let me try it again and then put some more of the %p. And then now we see that the sixth value, the last value on the stack, yeah, was the random value. Then how we can pass this is supply this and then copy this value and paste it. Then we got the group ID. So this is something like that you need to pinpoint like where the random is and then try to search for that. Yeah, and then like if you can identify where the random is and the relative to the like your current argument position in the stack to that variable, and then by just increasing number of directives, then it will eventually print out the value in the stack. So you can apply sequential read as a format string variability as a sequential read primitives. So if you can read the stack like that, then you can leak the stack cookie and also some of the other variables, return address, and so like you can break the ASRL. Yeah. So like in combination of that, like even if like the program is protected with the ASRL, DEP, and also for the stack cookie, then we can leak the stack cookie value. We can identify all the addresses spaces by breaking the ASRL, and then we can create the ROP chain, then like we can exploit the program. Yeah. So this is the sequential read example. Yeah. And then like we can also practice like the pointing the argument with the argument selection number exactly. So for example, we know that the random number is at the sixth position in the argument number. So in that case, we can put the $6 p, and it will print out the random number directly. Then we can use that. Yeah. So please make sure that like there is this kind of the syntax, so that you can select the argument order at here. Yeah. So you can skip the argument 1, 2, 3, 4, 5, and then directly print the sixth one by like placing the selector at here. So you can solve it like this, and also for the 64-bit, it will work the same. So the problem is that in 64-bit, we place some of the arguments in the registers, not the stack. Yeah. So we can supply up to 6 arguments in this registers, and then for the 7th arguments, 8th, 9th, 10th, and then like more arguments, we need to put on the stack. So even in the 64-bit architecture, so for the first, the format string, and then the 5 additional arguments will be passed through the registers, but the overflowing thing will be on the stack. Yeah. So that's why we can also apply like the %p, %p, %p to read the the format string variability as a sequential read variability. Yeah, and then we can eventually leak the random value. So let's just try it. So format string read, I just run it and then use some of the %p. Yeah. Then it printed out some of the values. And then the random value is A4, AA, A7, 3Z. So you can see that value at here. So the position is 1, 2, 3, 4, 5, 6, 7. Yeah. So it's at the 7th position. So in 32-bit, it was like a 6th position. So the stack is a little different how like the program uses for the argument passing and so on. So in 32-bit, like the random value was placed 6th argument position place. But in the 64-bit one, it's on the like a 7th additional argument. That means like it's just about like 16 bytes above the stack, because like for the format string and also like 5 other arguments will be passed on the register, so that they will not access the stack at all. And then the 6th argument is just the first one on the stack, and then the 7th argument is the second one on the stack. So it's the second one on the stack, and you can get the random number from there. Okay. Any questions up to this point? So because the printf mechanically like regard like even if like if we supply no arguments, it will regard like if there is an argument on the stack. So whenever it meets some of the directive, then it will just access the stack. So that's why like we can exploit the format string variability as a stack sequential read variability. And that's why we can leak the local variable. And then let's move on to next. So it's a format string read 2. And the challenge here is that very similar to format string 1. But another additional problem with here is that, so now it defines a struct variable var, yeah, and then it will read to the var.name. So let's take a look at how the struct variable look like, and then like we will store the name at here, yeah, and then there's a buffer, and then random value, and how it is actually placed, yeah, in the stack is that, so this struct will be placed in the opposite order because we will draw the stack upside down. So the random number will be around the top of the stack, and then there will be name and buffer, and then other, yeah, bytes, yeah, something like this. So our printf will work on the stack around here because we placed this kind of the big, so 64 byte for here and then 512 byte here. So this kind of the big object on the stack. And we will receive our input here, but the random value is here, while our printf will be working like around the down here. Yeah. So, but the problem is that, so this is around like the 600 bytes differ from like the here to the like the random number that we need to leak. But the problem is like we can only supply 63% P. So that means, so 63 bytes for percent P. If we supply something like percent P, percent P, percent P, percent P, something like this, then we can supply 31% Ps for this one. And then even if like we try to print out all the characters, it will only print around like a 31 numbers. So in 32-bit, so each percent P will print out 4 bytes. And then if we can print out 31 of the percent P, then the number of bytes that we can print out is a 124. So that means, so get back to this stack diagram. So our printf is working around here, but we can print up to 124 bytes. Then we can print up to somewhere here, not that much in the buffer, but it cannot reach to the random number. So by just using percent %p, you cannot reach to the random number. But in that case, you can use the argument selector in the $flag directive, and you can skip all these things. And as we do in like the $6 for the 32-bit, $7 for the 64-bit. Yeah. So if we can point some certain like the argument position, then we can skip these bytes and then just pick the random number and then print that out. Yeah. And to do that, we can also use some of the debugger information to calculate the address difference accurately. And let's do that. Yeah. And let's run the program with the debugger. And then let's disassemble the input function. And the first thing that we will focus on is like how it uses the read random, and then after the function called the return value will be stored in the EAX register. So this is the return value of the random. So this is the random value. And then that will be stored into EBP minus 10. So we can copy this, and then we can make a note. So random value is at EBP minus 10. Yeah. So we'll just make a note for that. And then run the debugger again. Disassemble the info function. Yeah. Then go to the printf. So we have a several printf here, and this printf prints some of the fixed string, maybe hello, And then this printf prints the first argument is EAX. Then that is coming from this one. Yeah. Some of the struct, yeah, add 4, yeah, something like that. So this is the printf that this is the printf that we sorry about that. I got just some of the weird warning on the Zoom that I was logged out. So excuse me. Yeah. So so what we will do is like if we can set the breakpoint here, and then we can take a look at which address will be printed out if we just use %p. Yeah. That will be the first argument. If we add more %p's, then we can check the value and then find those values on the stack and to pinpoint like if we just use %p, which value would be printing. So I will set the breakpoint at the input function plus 99. So I will set the input function plus 99 as a breakpoint and then try to run it. And then what I will do is I will just put maybe 5% P's. Then it will print out the 5 pointers. Then press enter. Yeah. So right now, so we set the breakpoint at the right before calling the printf. So from the stack, so this will be the format string that we have. So let's check. No, that's this value. Right? So this is our input. So this is the address of the format string. So what we do is what the code do is like the printf name, right? The name is the buffer that we can control. And then that's the first argument. And then if we apply %p, then it will print out the next block. So the expected printout will be FFD0 F818. Yeah, we will see that later. And then some other values are such as like these values. So we can set our target address as this one because no. Yeah, because like these values, like the 1, 2, 3, 4, 5, these values are like something that we are expecting to see from the output of the current running. So I will try to continue the execution, and then it asks us to guess the random. And then before that, we are seeing some of the outputs. So this output matches with this one. So %p first one, yeah, will be the printing this value. %p second one printing this value. Third one printing this value, right? And then 0, 0, that's why nil, nil. So we can know that if we use %p, the first one will print out at this address. So what we know is that, so this is the address that like we will the printf will print out if we use the first %p. And then what we will do is like if we will get the address of the random, then we can get the difference to get the relative position. So we will calculate that. And then to do that, right now it's in the read somewhere. So we need to return up to this input function. So because in the input function, there's a random value. So we will return to the context of the stack of the input function. So because we are at somewhere deeper in here. So to do that in the debugger, we can run return. So right now we are at the read cancel, no cancel, then return again. So now out here, return again, return again, return again, return again. We are at the scanf, then return again. Then now we are in the input function. Yeah. So what I want to check is what is EBP minus 0x10. Yeah, that's where the random value is stored. So the address of the random value is this one. And then address of the first %p is this one. And then if we can subtract these two, we can get the offset. So we get the values. So in Python, we can get this value. Yeah. And then it's 596. And then we can divide it by 4. So it says 149. Yeah. But we need to add 1 because like the index is not starting from 0. So this is for index 1, and then this is for like the index somewhere. Yeah. So actually I believe the value will be at the like the percent 150p. Yeah. So from the GDB and calculation, we got that value. Then we can try both like the 149 and 150. And let's try 149 first. So percent 149 $p. So it says nil, so that's not the random value, right? And then percent 150 $p. So it printed out something or look like a random value. If I copy and paste it, then it's correct. Yeah. So from the GDB, yeah, we can calculate the distance between the where current printf uses argument and the location of the random value, and then we can apply the sequential read kind of the primitive. We will use the format string variability like that, and by calculating the exact difference in address and divided that by 4, because in 32-bit machine we access the argument in 4-byte granularity, and that dividing factor would be 8 in 64-bit. Yeah, because we will use 8 bytes as a granularity for selecting arguments. Yeah. So after having that, you can have an exact relative index. Then you can apply that index as the selecting for the argument. And then after calculating the value, don't forget to add value 1, because the problem is that the index of this one is starting from 1. So that's why we need to add back 1. Yeah. So any questions for this challenge? So the previous one was like the random value was near the printf argument region. Then so with the small number of the percent %p, you can eventually leak this value. But in the second case, the gap between the printf and then the random value is quite huge. So with the percent %p, you cannot reach it. But by calculating the relative offset, yeah, in the addresses, and then divided by that, you can get the argument index, apply that, you can exactly printing out that value to pass the challenge. All right, let's move to the next one, format string arbitrary read 32. Yeah. Let's do format string arbitrary read for 64. No, I will just do all 32-bit for that. Yeah. So let's do this. And then in this challenge, so we are doing the same thing, they're guessing the random number. Yeah. And the problem is that now it will do read random here. And then read random actually reads the random value to the global variable. So then now the random value will not be in the stack at all. So with the sequential read, we cannot read the value. So the random value is not on the stack. And we have a format string variability here. Then can we read that and make the perfect guess for this one? So we can do that. And the reason is like the stack configuration is something like the printf will use an argument from here, but in the somewhere up here, we have our buffer here. And then because we can control all the data in the buffer, we can set the argument value as something like here, and then put that as the random value address and apply %s. Then it will leak the data. Then we can read the data, yeah, and leaking the random value. So we will do that. And to do that, we first need to get the address of the random value. So print address of the random value. So the random value is at 0804A0550. Yeah. So we will write a Python script. And then we know the random address of a random value is at here. Yeah. Yeah. And then we will run the p process. Let's copy the name of the binary. So we will run this program. Yeah. And so how it works is like the one line I need to type in, then hello something print out, and then can you guess the random rate? Yeah. So I can print receiver in the strip, and then I will make a guess. Maybe percent %p, percent %p, percent %p, percent %p. Then maybe I can make it as a buffer. And send line, buffer, receive line, and then the strip it, and then yeah. So I will just supply these 4% P's, and then let's see the result. So we can see these kind of the values printing from the stack. Yeah. But right now, the challenge is not the printing values in the stack, but we need to apply arbitrary write, arbitrary read. And to do that, so what I will do is like I will place a queue for the some of the start of the buffer. So for example, I will place A at the start of the buffer. And then if our %p prints out 41414141, and then that's the start of the buffer. So what we can do is I will put A here, then B here. So if we can see like the 41414141 42424242, then that's the start of the buffer. And then I will place a loss of %p like this. And then let's run this. Then we can see 41414141 42424242 here. And then another thing that we place is the %p space, %p space. These are %p space, %p space, something like this. So that you can see our buffer at here. This is the first, second, third, fourth, fifth, sixth, and seventh. So the seventh argument stores our value. Then what we can do is, so we know that this will be the argument, and then we know that %7 $p will print out that value. So let's try to run it. Right, the seventh argument is 41414141. Yeah, that's good. And then what we will do next is, so we will change the first 4 bytes as the address value. So P32 address random value. Then we will use the address of the random value as it's the seventh argument. Then right now we are not doing the arbitrary read, but we print out with the %p. Yeah, so if we can see that the same address is printing, then the argument placing was correct. So we can ensure that the seventh argument is this one, and then if we change that to %s, it will try to read the data from there. And then let's change that to s, and then run it. Then can you see like some of the weird printing at here? Yeah. So that's actually like printed by like a %s. And then let's try to check like what kind of the values are there. So to do that, so this is the response, right? And then we can print representative, some representation of the response. Then we can see some of the binary text in there. Then let's run ex.py, and then it leaks some of the values around here. Yeah. So if the random value is the A5 something, FCDE, then that's the thing. So A5 something FCDE, right? That's right. So we have the random number here. Yeah. And then let's take a look at the how can we cut this string. So 5 bytes, 6, 7, 8, 9, 10 bytes. So we need to cut 10 bytes of the string, then we can get the last of the 4. And maybe like we can just cut the last 4 bytes from the random number. Then what I will do is response, just cut the last 4 bytes, and then that will be the answer. And then I will post the answer. Yeah, but this is not the way that what we need to do is that we need to make the answer as a binary, the hexadecimal string. So to do that, this is a binary string. So we need to change this as an integer with U32. And then by applying hex, then we can change that as a 0x or something like a string. So if I run it, then it says, I guess the random correctly. Yeah, because that will like use this as a random number. Yeah, and then now we can get the group ID. So the difference of this challenge from the others is like the other two was like the random number was on the stack. So using the sequential read, you can leak this value. But right now the random value is somewhere like the global area. But using the format string variability, it's an arbitrary read primitive. You can point this and then leak the value. Any questions for this challenge? So because the value you type in the buffer, for example, AAAA, BBBB, those kind of things will also be on the stack. So you can select, you can eventually select those as an argument. Yeah, and then but just like get the position of the argument. And then if you can access that, yeah, with the argument directive, and then change the value in that buffer into the address, then change that as a S, then it will dereference the pointer argument as a pointer and then leak the data. All right, let's move on to the next the challenge, the last demonstration for today. Yeah, this one, arbitrary write. So that we can also apply the arbitrary write using printf with the %n directive. And %n directive is some of the weird directive, but what it does is like it will record the number of the printed character at the current printf call to the some of the integer variable. But that variable will be passed as the address. So what it does is like it will dereference the argument as an address and then write the value in there. So we can actually dereference the pointer, so we can use it as an arbitrary write because we can control the argument arbitrarily. And to check the format string arbitrary write 2, so what it requires is, so that there will be the global random value here, and then that will be the get the return value of the global random. So the random value will be stored here, but the winning condition is that that value need to be this Facebook, FACEBOOC. Yeah. So it's randomly generated, but the value need to be this one. So we need to do some kind of the magic here. Yeah. And then like what kind of magic we can do is like we can exploit this format string variability because there's no buffer overflow variability here. Yeah. So we will use the format string variability to change this value and bypass this check. Yeah. So to do that, we need to apply arbitrary write to this value. Yeah. And change this value into this value, Facebook. And let's do that. Write an exploit script. And then I need to copy the name of the program because I cannot memorize that. So copy this. So p.elf the symbols. So we are searching for global random, right? right? The name is a global random, right? So we need to get the address of the global random, addr random. And let's check if it is running correctly. So yeah, we got the address of the global random here. Yeah. And then what we will do next is like the and it will ask a name, and then we can supply buffer here. So some of the %p's. So my typo. So small %p, and maybe we can place a b b b b to identify the argument selector order. Yeah. Then p dot send line buffer. Then print. And then I can store this as a response. Then print response. And p dot interactive. So now we can figure out the argument order. So 1, 2, 3, 4, 5, 6, 7. So the %7p will print out the first part of the our buffer. Yeah. So that's the thing. And then what we can do is like if we know that the buffer is at the %7p, right? And what we will do is like if we know the address of the random, we can put the address at there, and then %p $7n, then it will write the value. But then what kind of the value we would like to write? And our target value is Facebook. Yeah. And then get to do that, we need to make the number of the character printed as a then number. And then if I change this into decimal integer, then it's around the 4.2 billion. Yeah, many characters. Yeah. Then I can do percent this much character and x and %n. Maybe I will just test %p first. What will happen if I run this? I will try to do that. So it has an exit code, something weird. Yeah. And then let's just try. Yeah. So if we do like this kind of thing, then the printf actually ignores this kind of the big number. Yeah. Actually, the printf will not accept a number like the bigger than certain number. So yeah, that's why. Yeah. So the printf is completely ignored here. Yeah. So we cannot put this kind of the big number. Then how can we write Facebook? Then what we can do is, so what we need to do is we have 4 bytes. Maybe we don't know the values, so we can put it as a XX, YY, ZZ, WW. Yeah. Suppose we have these 4 bytes and then some more bytes in the addresses, and then you can think it as this as the address of the global random. Yeah. And then what we will gonna do is we want to override the 0C, B0, C, FA to make these values as the random value as a Facebook, FAC, B0, OC. Yeah. And then we don't care about the rest of the values. And then how can it do that is like that. We will write B00C here. And then we can also write FACE at here. So that we can split the write into 2. Then we will write the 2 addresses, and then we can split the addresses by like the offsetting by 2. And then we will write the last 2 byte first, and then the next 2 byte later. Yeah. So to use that technique, we needed 2 addresses. That's actually the address plus 2. Then to actually test that, what I will do is like I will do %7p and then %8p. And it should print 2 addresses, the random address and then random address plus 2. Let's see that. So now we are seeing that the random address is here. Yeah. And then random address plus 2. So it's a hexadecimal number. So 8 plus 2 is 9a. So A. Yeah. So now we have the address. And then to overwrite the values, what we will do is like right now, we printed 8 bytes up to this point. So from here to there, these are 8 bytes. So we printed 8 bytes. So we need to print 0xb00c minus 8 more bytes. And then let's calculate what is the value. So that's 45060. So what we will do is basically we will print out this much character to make the entire print as a B00C. So from here to this point, we print out B00C characters. Yeah. Then we can just fix the string, cut the string out here. And then we need another printout. And then because we have a BOC characters, then we want to make the entire printout as a FACE. So we will print out FACE minus B00C, this more characters. Then let's calculate that first. Python FACE minus 0xb00c. And that's this number. So we will print this more characters, percent this x, then $p. So right now I will just test with the $p. Let's see the output. So right now that we are not sending the exact value, so it has like some of the error, but this is a printout as a %x, and then %p actually print out the target address, A048, and then the second %p printed out the A04A, so the address plus 2. So we are trying to writing the 2 values, something like this. And then like these are the some of the empty white spaces that is added by like these kind of the 2% x's. Yeah. So that we can match the number of the bytes that we printed to the byte values that we need to write, and then overwrite that value to the first 2 bytes, and then second 2 bytes, and after printing the more values to compose a FACE, BOC. Yeah. So let's try to change this %p into %n, and it will overwrite the value. So now it says great. That means our format string vulnerability successfully changed the target argument, the value at the target argument. Yeah, value pointed by the target argument. Yeah, right. Yeah. So by dereferencing that with %n and by writing the number of the printed bytes into that data. Yeah. So we can change. We can apply the arbitrary write by using these kind of the techniques to exploit the format string variability. Any questions in this approach? So we have seen like all 3 use cases of like using format string vulnerability as a sequential read primitive. and then using format string variability as an arbitrary read primitive. And then finally, we have seen the case of like using the format string variability as a arbitrary write primitives. Yeah. So that we can apply all three. And then in the next lecture, we will learn about like how we can exploit these primitives as like a code execution to achieve the code execution. So the topic focused on in this lecture and then today is like the learning about like the translating the format string variability into either one of the primitives, sequential read, or arbitrary write. So any questions? All right, maybe you guys need more time to take a look at the challenges by yourselves. Yeah, and please feel free to take your time and then like ask questions via Discord. Yeah, and thank you for your attention and thank you for participating in this Zoom meeting. And let's conclude the tutorial here, and then I will upload the tutorial video in an hour later.
Professor,
Yes.
I have one question about
Okay.
the because we have used the like just like sorry, I just type this one in BOS. Use like this, and the other one is ELF. Then use this one MBOS. What is the
Yes.
difference between these two type
So
method?
P is process, right?
Mm-hmm.
And then when we load the process, then p.elf is actually so we do something like a process, something like this.
Mm-hmm.
And then p.elf will contain the ELF of the A. Yeah.
So the first one is based on the let's binary file, but the second one maybe is a real library address.
No, you can also open the binary file too. Yeah. But the reason why we can get the library addresses here is like I supplied the library location, library file here, yeah, to create the different ELF object. So the p.elf will hold the binary file of the target, the vulnerable program itself. And then if you load the library file here, and then this E, yeah, will be the ELF object for the library file.
So, Professor, did you just did you have any motion on your screen? Oh, okay.
No. So the answer is like the E as an object, like if that opened the library file, then it will just point to all the library symbols, right? But the p.elf will be will always be the target binary, yeah, that you run.
Okay.
Yes. All right, let's finish it here and then have a great weekend and then have fun with the challenges. And then it's a deadline on the June 3rd, so we will have plenty of time for solving all these challenges.